We have spent the last couple lessons talking about different aspects of polynomial functions, which built on that first lesson on power functions. What we're looking at today are rational functions. Now, the way that rational functions relate to polynomial functions is that a rational function is really just the ratio of two polynomial functions. So let's say that we have function r of x, and we have two polynomial functions p and q. So if r of x is the ratio of p of x over q of x, then r is a rational function. And we are going to assume that that denominator is not q of x equals 0. That's the one stipulation we need to make. Okay? So just getting us started, we're going to identify whether the functions are rational, and then if so, we need to write them in that form, p of x over q of x, basically the ratio of polynomials. So if we look at the first one, we have basically two rationals. So if you think about the warm-up we did several classes ago, we do need to make a common denominator and write this as a single rational. And then that will give us the ratio of polynomials. So our common denominator is going to be 6x squared. So the first rational is missing a factor of 3. And the second rational is missing a factor of x squared. So we're going to multiply top and bottom by the factor that it's missing. So that gives us 3x cubed over 6x squared plus x squared over 6x squared. Then once we have that common denominator, we can write this as a single rational expression. And then doing that, then we have accomplished our goal to write this as a ratio of polynomials. So we have a polynomial on top, we have a polynomial on bottom. So this is a rational function. If you look at the second one, this is pretty close to being a rational function, but there is one thing that actually makes it not. And you might be seeing it, but what it is that exponent of x. So because you have that in your numerator, that makes the numerator not a polynomial. And because your numerator is not a polynomial, then your function f cannot be a rational function. Our main focus today, similar to how we looked at the long run of polynomials, we are going to look at the long run of rational functions. And actually, it relates very much to the long run of polynomials. Basically, what's going to happen is that in the long run, every rational function is going to resemble a power function. So let's take, for example, what we're given here, function f of x. We have f of x equals 6x to the fourth plus x cubed plus 1 over negative 5x plus 2x squared. Now, if you remember back from our discussion in polynomials, we know that the leading term of a polynomial determines the long run behavior. So when we're looking at this, what we can say is that the numerator of that rational function resembles 6x to the fourth, and the denominator because remember we want the leading term, even though this isn't written first, the leading term is that 2x squared. So the denominator resembles or behaves like 2x squared. So then what we're going to do is we are going to take, because we're really looking at a rational function and the ratio of those, we are going to say that the function f in the long run kind of looks like 6x to the fourth over 2x squared, which if we simplify that, that's 3x squared. So basically, in general, in the long run, your rational function is going to be given by y equals, and then you're going to take the leading term of p, which is your numerator, over the leading term of function q, which is your denominator. Very much like what we did here. We took the leading term of the numerator over the leading term in the denominator. Then this gives us the function of our rational in the long run. So a couple of examples here working with this. It says for a positive value of x, describe the long run behavior of each rational function. So what we're going to do, again, we're looking at the leading term of the numerator over the leading term of the denominator. So the leading term in the numerator is just that x. Taking that over the leading term in the denominator, which is also x. When you simplify that, x over x, we know is just 1. So we would say for large values of x, the function r of x equals x plus 3 over x plus 2 looks like or resembles y equals 1. Okay? Let's look at the next one. Same type of thing here. We're going to take the leading term of the numerator, which is 3x, over the leading term in the denominator, which is x squared, and we'll simplify that. This gives us 3 over x. So again, for large values of x, g of x looks like y equals 3 over x. So this is kind of the response I'm looking for when you're asked to describe the long behavior of a rational function, okay? Then the very last part of this lesson is identifying horizontal asymptotes of rational functions. To do that, again, we look at the long run behavior of the function. So we're going to find the horizontal asymptote, if it exists, of the rational functions. So we're going to do that for example 1, which we did up here. So basically, because the long run of this first example was y equals 1, that's also the horizontal asymptote. Similar type thing for example 2 from above. We are going to look at the long run behavior. The long run behavior of example 2 was y equals 3 over x. But what we need to look at, basically, is the horizontal asymptote of this function. So if you look at this on your calculator, you will see a horizontal asymptote at y equals 0. So the horizontal asymptote is y equals 0 because it's the horizontal asymptote of the long run behavior. Okay? Look at the last example. So here, the long run behavior is 1 over x squared. If you look at that function, the horizontal asymptote again is y equals 0. There are some little tips and tricks to help you identify horizontal asymptotes, and this is actually how this is taught in Algebra 2. And it has to do with the degrees of the polynomials on top and bottom. If the degree is bigger on the bottom or in the denominator, your horizontal asymptote will be y equals 0. So just like it was in this example, the degree here is 2. That's bigger than the degree on top. If the degree on top is bigger, then there is none. There's no horizontal asymptote. And then if the degrees on top and bottom are the same, then you just take the ratio of the coefficients. So this would be like example number 1. Your degree on top and bottom was the same. So the long run behavior essentially ends up being here 1. That's the ratio of those coefficients, 1 over 1.